Good morning. I'm Walter Grayman, representing the Environmental and Water Resources Institute, EWI's WDSA History Project. The purpose of this project is to document the history of water distribution systems analysis. An important part of the project is a series of interviews with engineers, modelers, researchers, and practitioners who have made significant contributions to the field of water distribution systems analysis. Our interview today is with Dr. Yehuda Kleiner. Yehuda is a Principal Research Officer at the Construction Research Center of the National Research Council of Canada. Over the past quarter of a century, he has been a leader in the area of reliability and risk in buried infrastructure systems. This has resulted in over 35 publications in refereed journals in this area. This interview is being conducted on July 23, 2018 in Kingston, Ontario at the joint WDSA-CCWI conference. Yehuda, can you tell us how you first got into the field of water distribution systems analysis?
Good morning, Walter. First of all, thanks for having me here and making the time to listen to what I have to say. And I must say that your initiative of recording some of us for posterity is quite admirable. So we do appreciate that. As for your question, how I got to this field, it's actually somewhat embarrassing to realize how serendipity plays such a significant role in at least my professional career. Born and raised in Israel, I, like everybody else, joined the army after high school. And it so happened that my army service was a special service combined with service in the kibbutz in Israel. And it so happened that the kibbutz that I went to a few years prior acquired a share in an irrigation company called Netafim Irrigation, which was then just a starting company of drip irrigation that was invented and developed in Israel. 35, 40 years later, and now it's the largest drip irrigation company in the world. So I'm proud to say that I was one of the first ones there. And it so happened that out of our entire group, they identified me as someone to be trained to be an irrigation designer. And so fresh out of high school, without any prior knowledge or anything like that, they started training me as an irrigation system designer. And this is how it all started. When I finished my army service, I already had a direction of sorts, and so I continued to the Technion, the Israel Institute of Technology, to do my Bachelor of Engineering in Agricultural Engineering. There is an agricultural engineering faculty at the Technion, and I took the direction of soil and water. And in 1983, I finished, and pretty soon after, I was sent by the company to the United States, where I worked as a project engineer for 3 years in Phoenix, Arizona. We had quite a few nice large projects there, and afterwards I went back to Israel. Now, at that time I was already an engineer, and I worked for engineering firms, mainly consultants in water supply system design, planning, sewage system design and planning, and it was your run-of-the-mill consulting firms in Israel. At some point, I decided that I was ripe to go and do my master's, and I went and did my master's again in the Technion, but something completely unrelated in industrial management. And after I finished that, in '92, we moved to Canada. My wife is Canadian. By the way, I met my wife with the same serendipity in the kibbutz in Israel. She became my wife later. And so we moved to Canada. And when we moved, it was an opportune time to continue my education, and I went to the U of T, to the University of Toronto, to check out the possibility of continuing to do my doctorate. And again, serendipity kicked in, and Professor Barry Adams happened to be there. It was in the summer. And we got to talk, and I wasn't your run-of-the-mill student. I was already a mature student with some experience behind me. And he said, "Yeah, sure, come and we'll work together." And we did. And we decided later on that my thesis topic that I was going to work on was in distribution system optimization, more specifically renewal optimization of water distribution systems, which I finished my PhD thesis in 1996. And then again, serendipity kicked in. I was invited by the NRC to give a presentation, a short presentation about my thesis. And little did I know that this presentation ended up being an interview, a job interview. And so after this presentation, I was offered a job at the NRC, which I accepted. And 22 years later, here I am.
Fascinating.
Yeah.
With your upbringing in Israel and your education there, Israel is known for both managing and I think recognizing the value of water. Did that influence your later career?
Well, it did indeed. Israel is known for having very scant water resources, and one of the reasons I went into this direction to soil and water in agricultural engineering was it was quite a bit of serendipity, but also the realization that this is a field in which there is a potential to contribute and to achieve quite a bit. So it was also always in the back of my mind that the issue of water resources and things that were related to water resources would be something that I would want to do because there is so much to do and it's so important.
So for the past, I guess it's a quarter of a century now, you've spent much of your research career working in the area of pipe and infrastructure reliability and risk and some related fields. Can you identify some of the highlights of this work in this broad area? And also how the state of the art of this field has changed over this period?
It's interesting. When I started working at the NRC, we had a group that was created by my colleague and good friend Balvan Rajani, Dr. Balvan Rajani. It was called the Buried Utilities Group. And before I joined, they focused on the physical aspect of pipe soil behavior and interaction in the ground. When I joined, I added the dimension of a systems view, what happens to an entire system in the ground. And we set out to do a little bit of what's the word I'm looking for? Academic research. But because there was quite a bit of academic research taking place already, we wanted to position ourselves in the interface between academics and practice. And so we tried to focus more on the practical aspect of research and bring academic knowledge to the user so that the end users, the practitioners, the municipal engineers, the consulting engineers could use what is developed by the academic research. I don't know to what extent we actually succeeded in doing that because surprisingly enough, the uptake of the industry of academic research and even decision tools that were developed by academic research is surprisingly low. It's a low rate. At least that's what I discern now, looking back. I would expect with all the resources and all the effort that was going into this field, and not just by the NRC, the National Research Council of Canada, but some American firms, the Australians, the CSIRO, the British, everybody started paying attention to asset management, infrastructure, or water infrastructure asset management. We worked a lot with the Water Research Foundation. Well, now it's known as the Water Research Foundation. At the time when we started, it was known as AWRF, the American Waterworks Association Research Foundation. We did quite a few projects with them because they had the ear of the practitioners. Their members are actual municipalities, and so we reasoned that their members would articulate a direction for which they see value and need. And so we aligned ourselves with them, and we delivered quite a few projects on these needs as they were perceived. Some of these projects were more theoretical, some were more practical, but in every case we tried to add a deliverable to the project, which was a computerized tool, with the thought that if we automate everything that we want to achieve, practitioners will be more readily, the tool will become more available and they will be more ready to implement it. To our surprise, it wasn't the case. There was some uptake here and there and some interest here and there, and maybe some software. There was some interest from some software companies such as Bentley, such as Innovize, maybe to take some of our research and incorporate them, but none of it actually panned out. And we were contacted by practitioners to do individual projects here and there, but the mass uptake of what we developed, as far as I can tell, has not materialized, which is a little bit surprising and maybe something to think about and to do in the future to get the practitioners actually use all these wonderful tools that we supposedly developed. We employed all kinds of approaches. We tried the traditional statistical approaches. We tried fuzzy mathematic approaches with the thought that a lot of the practice that was going on, such as, say, condition rating of pipes, is quite subjective and frankly speaking, fuzzy. It's not crisp. It is a subject of interpretation. So we thought that fuzzy mathematics, which lends itself very well to this type of non-crisp and ambiguous evaluations, it lends itself well. So we thought if we develop something at the base of that type of approach, it would be maybe more usable. It was uptaken by some people, mainly consultants. Someone at ACOM, in one of the groups of ACOM, adopted it, or at least parts of it, but there was no a global adaptation of that, and so we later on reverted back to the traditional statistical approaches, with the thought that maybe the market wasn't ready for the more advanced, I shouldn't say advanced, but the more exotic types of mathematical approaches. Something else that I noticed is, whereas in the last 15, even 20 years, the knowledge industry is increasingly using data in more sophisticated way. You look at companies like Google, for instance, 90% of their business is data, is mining the data, analyzing the data, and delivering some products based on some of the data analysis. And you would expect that in very technical fields, such as our field, engineering, or water systems, etc., you will get the same trend. Now, in some cases, we do get the same trend. For instance, there's a big movement now to put a lot of sensors in the water distribution system to get a lot of continuous data, pressure data, flow data, sometimes other sensors, and to create some knowledge out of these data, put them together, fuse them, and then conclude something about the operation of the system. And this is true, but it is true mainly in the operations, on the operations side of the water distribution system, not so much on the renewal planning. And I think the reason is that the data that is required for renewal planning are not the data that you collect from sensors. It is data about the history of your assets. You see, in modeling, trying to anticipate how the water distribution system will behave, we don't know. It's trying to predict the future. And we're trying to predict the future based on the behavior in the past. Unfortunately, this is although it's a little bit of a stretch that something will continue, the trajectory will continue in the same way into the future, but this is the best we can do. We can't do anything else. And so we're looking, in our field, in asset management, we're looking for historical data about the system, about the behavior of the pipe, in order to make informed decisions. I don't want to say optimize, because we can't optimize these things. There's too much we don't know. But the objective is to make well-informed decisions. But even to make these well-informed decisions, you have to go into the past and to discern what happened to the system, to the assets, and what is the actual trajectory that we've been witnessing in order to make a reasonable trajectory into the future, to anticipate and to make the best decision possible. And the data that we have about the history of these pipes is very, very spotty. There are some water utilities that are better than others, and some water utilities that, if I told you, I don't want to embarrass anybody, it's just they don't keep anything. And even when they kept it, sometimes they just destroy it because somebody decided that these data have no value, and they just burn them, destroy them. We found many cases like that, and it's quite embarrassing, but that's life. And so this is the big thing, is the data, the historical data. Can we produce it? Can we go back and produce it? Can we take the data that we have and clear? A lot of the data that we do have is inaccurate, is faulty. It needs a lot of cleansing. It needs a lot of verification, etc. So this is also something that is required in order to do a decent asset management projection, and it takes a lot of resources. And unfortunately, in the world today, especially in the world of municipal operations and engineering, the urgent trumps the important. So resources are put on solving the urgent problems rather than the important problems that determine the future. Does this answer the question?
Well, certainly a start. You've worked in and with academia, water industry, government. Do you have any suggestions for how those groups could better interact to achieve some of the problems, or to ameliorate some of the problems that you've laid out?
Right. That's right. We worked with everybody, as I said, with the research foundations, with municipalities, both in Canada and the United States and in the UK, and even in Australia to some extent. We worked with other research institutes. We worked with academia. There is room for everybody, and everybody has a significant contribution to make. And of course, the thing is to bring all these contributions together in order to maximize the impact. Is there a better way to do it? What I've observed in the last quarter century, as you put it, is that everything depends on the champion. So if you find in any organization, you find one single champion who realizes that what is doing, the connection or the topic, is important and is willing to put him or herself out there to champion the cause and to put the resources, things will progress and progress well. Organizations on their own don't do anything. It's the champions within the organizations that you should identify, tap, engage, and then you'll get results.
Thank you. Any optimistic views on where you see this field and your particular aspect of the field going over the next 10, 20, 30 years?
Well, I have some thoughts. As I said, data are the big thing. I think that with the advance of computers, computing power used to be a hindrance, but it is no longer. I remember when I started going in the field, I programmed on my little sharp calculator, a Hardy Cross program to solve some looped networks, and it would take 10 minutes to solve maybe 4 or 5 loops. Now, obviously, with tools like UPA-Net and all the computer power that we have, this is no longer the issue. I should say that in optimization, I'm going to mentioning this wonderful word, optimization, the dimensionality of the problem of optimizing renewal of water distribution network is immense. If you think about it, even a small town like Kingston, in which we're here, they have maybe 1,500 kilometers of buried pipes. 1,500 kilometers of buried pipes arranged in maybe 20,000 arches with, I'm just throwing the top of my head, I don't know that for sure, but just as an example for a relatively small system with thousands of arches and hundreds or maybe thousands of nodes. And for each arch, which is a pipe in the node, you can renew it anytime between now and maybe 30, 40 years of planning horizon, and you can renew it with 2 or 3 or 4 alternatives. In other words, the same pipe, same size pipe, maybe a different size pipe, or maybe reline it and not replace it, etc. So there are many possibilities, and remember that every time you renew a pipe or you change the properties of a pipe, you affect the entire network around it. The close proximity could be affected significantly, the far proximity maybe less significantly, but when you change the hydraulic properties of one pipe in the network, theoretically you change the entire setup of the network. So every little change that you make has to be revalidated through the entire network. And so there are so many combinations and permutations. The solution space of this problem is immense. And it's combinatorial, it's not smooth, and it doesn't behave very well. And so you cannot use techniques like steepest descent or things like that to get the optimization. You have to go to techniques that look for solution in combinatorial space, such as genetic algorithms and others. Do you get optimization? How do you validate if it's optimized or not? You can't validate because you cannot elicitate all the possible solutions, so you don't have against what to validate. And so it is, from a computational point of view, it is a challenge, although there are tools there that allow us, again, maybe not to optimize, but to give a reasonable solution for the future. So although computation is not a hindrance anymore, but it's not trivial. It still needs to be thought of. But then you have the assets in the ground. Now, how do you determine the trajectory of the asset in the ground? Right now, you just look at failure history and you try to project something into the future, but is that enough? Is failure history enough? Maybe you have to go in and, all these assets are all buried. They're out of sight, out of mind. We don't really know what is going on there. And so how do we get good understanding of what the condition of the pipes are? So there are non-destructive testing technologies out there, but they're very expensive to use. And so currently, the economics is such that these techniques are used only in large transmission mains where the cost of failure is high enough to justify the cost of rigorous inspection and maybe a more thought out solution, a more thought out planning process. Hopefully, as non-destructive testing methods become more mainstay and are implemented on a larger scale, the cost will go down, and then even smaller pipes will be inspected in some rigorous manner, and then we'll have a better understanding of the trajectory of the condition of these pipes. And then we'll be able to, again, don't want to say optimize, but have reasonably good decisions about renewal of the smaller pipes as we have now on larger pipes. Now, that doesn't mean that today we make the best decision on larger pipes. Balwant and I just finished a project for the Water Research Foundation to look at historical data and make some good decisions about the deterioration or the renewal of large pipes. Hopefully this will be uptaken, and it needs to be uptaken not just by practitioners, because a lot of these models are as good as the data that are used to calibrate them. We need to get the data, and we need to get the data not only from the practitioners and for the owners of the assets, but also from the vendors of these non-destructive testing technologies, because you have things like reliability of detection. I mean, these detection systems are not perfect, and so they have a probability of detection, they have probability of false positives, they have all these things that you, in order to make good decisions, you need to take those into account. And the data are not all there, even from the vendors. And when the vendors give you data, maybe they have their own set of criteria by which they create those data. It's ideally, we'll get the data both from vendors and from users of these technologies that do post-mortem, and then they come up with, actually results of these non-destructive testing and some validation to see what is the accuracy of these NDT, non-destructive testing technologies, in order to get a better understanding and to incorporate it into the economic analysis of how much does it really cost you to inspect, and if you don't inspect, how much is it likely to cost you in terms of damage or damage avoidance, etc. So I'm hoping that everybody will come together and will create some kind of a large data repository for people to use and to obtain results with which they are much more comfortable. Maybe something like you guys are doing, creating a repository of some historical aspects. Someone needs to take the flag and run it with creating the repository of real data for the benefit of the field.
Anything else you would like to add? This is for posterity.
Well, it's been a fascinating trip, fascinating journey, and hopefully it's not over yet. Although in the last 5 years, because of some structural changes at the National Research Council, I personally focused less on water distribution systems. Now we're doing more research in water and wastewater infrastructure systems in the Arctic, in the Canadian Arctic. And we're also looking a little bit at climate change impact on water and wastewater systems. I'm still, the issue of water distribution system is still closest to my heart. So I'm still there and hoping to continue to contribute.
Thank you very much for taking the time for this.
My pleasure.